We're continuing on in chapter 14. Maybe we'll get into 15 as well. Okay, so we are in sort of the home stretch here. We started talking about the last three chapters, which are carbohydrates. So remember again, this material here on carbohydrates will not be on our exam on Monday. It obviously will be on the final. So we got carbohydrates and lipids and proteins to go, I think. And so we started talking about carbohydrates. Carbohydrates are basically compounds that are made up of carbons, hydrogens, and oxygens. They are kind of referred to as sugars. There are a couple different sort of types of carbohydrates that we started talking about a little bit. We have monosaccharides. We also have disaccharides, which are basically two sugar molecules together. We'll talk a little bit more about those today. And then polysaccharides, which are a whole bunch of sugar molecules together. Essentially, they're all put together by taking out water, and that's how we sort of put them all together. There's also sort of two types of carbohydrates that we saw. One really has like an aldehyde group, like we saw in organic chemistry at the top of it. So it has that carbon oxygen double bond with the H. So it has this group here. That's what's known as an aldose, again, kind of like an aldehyde type of carbohydrate. We also have that carbohydrate that has really that ketone group, very much like we saw in organic chemistry. And that is what is known as a ketose. We also could sort of classify carbohydrates based on the number of carbons that they have, like triose, tetrose, which is 4, pentose, hexose, and so forth. And the other thing we talked about is a couple of things. We talked about the idea of a lot of times carbohydrates are sort of drawn almost in line structure, and just kind of like in organic chemistry, everywhere sort of crosses, those are carbons. A lot of times the most oxidized group there is on the top. On the bottom, usually we'll have sort of this group sort of happening. We also talked about chiral carbons and chiral molecules. So a chiral carbon or a chiral molecule is basically a carbon that has 4 different groups attached to it. So when it does have 4 different groups attached to that carbon, that's what's referred to as a chiral carbon. It also means that when you take the mirror image of that compound and you pull out the mirror image from the actual mirror, even if you rotate it or move it around, it will not superimpose on each other. So they will not fit sort of perfectly on top of each other, even with rotation. Now, if you have something that's an achiral sort of carbon, that's where you have a carbon that does not have 4 different groups attached. So we saw a couple of examples where we had maybe a couple of hydrogens on the same carbon. And the resulting of that is because you really don't have 4 distinct groups on that carbon, when you do put it up to the mirror, the reflection that you see back is a mirror image that actually can be superimposed. So again, that mirror image, that's something from an achiral compound, you can rotate it and get it to fit perfectly on top of each other. Again, chiral compounds are, as we saw last time, kind of like our hands. So again, if you put your hand up to the mirror, you basically have your other hand facing back at you. And if you pull out that mirror image, you cannot rotate your hands in any way that they fit perfectly on top of each other. And by perfectly on top of each other, clearly if you do this, they sort of fit, but they're not exactly superimposable. Again, one's palm up, one's palm down, so they don't fit exactly the same way. And that's what we're sort of talking about when we talk about a mirror image that can be superimposed. They have to be perfectly identical to each other in terms of their orientation. They technically got to fit perfectly right on top of each other as well. Excuse me. So I think where we left off is right around here. We also talked about some structures like glucose, fructose, galactose. Again, as I mentioned last time, you do need to be able to identify certain structures. As I mentioned, I don't think you'll be asked to actually draw the structures, but if those structures are sort of provided to you, you need to be able to recognize them as something like glucose, like I said, fructose, and so forth. I think the last thing that we sort of talked about as well is the idea of D and L, sort of isomers, D being right and L being left. And what we're referring to is the last chirocarbon in a carbohydrate from, say, the carbon-oxygen double bond, the last chirocarbon, where that OH group is at. So if it happens to be here on the right-hand side, then that would be the D. If it happens to be on the left-hand side, that would be the L version of it. L for left, D for right, basically. And we're looking for that last chirocarbon from really the carbon-oxygen double bond. Lastly, as well, that carbon-oxygen double bond, much like in organic chemistry, kind of the functional group. So it is the one that gets the priority in terms of numbering. So wherever that carbon-oxygen sort of double bond is located, I won't say it will always be carbon 1, but it should have the smallest number. And the reason I won't say it will always be carbon 1 is because in a ketose situation, it most likely will be carbon number 2. But in an aldose situation, it would be carbon number 1 in that particular case. Any questions on that there? Okay, so what we're going to talk about now is a lot of times what happens is these carbohydrates are not always sort of in these straight chain structures, if you will. Sometimes they do sort of fold up on each other, and they do make cyclic structures. So cyclic structures, like we see on the screen here, are basically like in organic chemistry, you know, some of those like 6-member rings, maybe like 5-member rings. So they make very similar sort of ring type structures. And it is a result of, you know, basically, you know, one part of it kind of folding in on the other, very much like how, you know, alkanes come together to make those ring type structures. Now, when these guys do make these ring structures, they typically will make one of 2 types of rings, if you will. So one ring looks very much like cyclohexane, which, you know, cyclohexane is this sort of 6-member ring. But the difference is there is actually an oxygen in the ring. So instead of actually being 6 carbons like we saw in organic chemistry, it actually makes more of a 5-carbon ring. And each of these guys here, 1 carbon here, 1 carbon here, 1 carbon here, 1 carbon here, and 1 carbon there. The other sort of ring situation that occurs is one that makes like almost like a cyclopentane ring that we saw in organic chemistry. Again, it also has an oxygen that gets inserted into the ring. And instead of 5 carbons, it actually ends up being 4 carbons in this ring. So these are all carbons here. We're going to put little lines. So how do they sort of fold up on each other? How do they sort of make those rings? For example, if we had a carbohydrate where, let's raise this so I got somewhere to scribble. So let's just say we looked at a carbohydrate such as this here. And we have, say, an OH here. Oops. We'll do an H here. OH here, actually, an H here. We'll do an OH. And we'll do an OH over here as well. So what typically happens, especially in the case of an aldose like we have here, is if we count the carbons, this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5, which I drew in a bad spot there. But essentially what will happen is a lot of times carbon number 5, which is right around here, will actually go up and connect with carbon number 1. And in this case, it's actually going to connect where the carbon-oxygen double bond is located. So in the case of an aldose, it is carbon number 1. And when you do that, you get basically this ring formed when that guy closes up on each other. So how do you know you get that many carbons? Because you literally can count how many carbons are part of the chain. So this is 1 carbon, this is 2 carbons, this is 3 carbons, this is 4 carbons, and this is 5 carbons. And that's how come we end up with this sort of 5-carbon ring that ends up here from those 5 carbons as they close in a ring. You'll also see that this group right here is not part of that ring being formed. And as we will see in a second, it actually ends up, I'll just draw it way, way longer than it needs to be just to clear all the writing. It actually ends up at that location all the time. So this is carbon number 6, usually will end up right about there in terms of its location. Now, when we number these guys, we do kind of go backwards. So this is 6, this would be carbon 5, carbon 4, carbon 3, carbon 2, and carbon 1 coming this way. So we kind of go into the ring and go counterclockwise in terms of the numbering of the carbons, and those correspond obviously to our straight chain type numbering. Now, how we get to say a cyclic structure like what we see here on the right is, for example, if we take something like this guy. Go one more here. I won't draw all the other stuff for now, but we'll just draw it like that. And again, if we go here, this is carbon 1, this is carbon 2. That's carbon 3, that's carbon 4, that's carbon 5, and that's carbon 6. What's going to happen in this case is sort of the same situation. That last kind of chiral carbon here at number 5 is going to go actually to carbon number 2 in this case. And that is because that is where our carbon-oxygen double bond is located. And when we make this ring structure, what ends up happening if we just sort of count everything, we have 1 carbon as part of the ring, 2 carbons as part of the ring, 3 carbons as part of the ring, and 4 carbons as part of the ring, which are the 4 carbons that are represented here. Much like the other one, we also see that this 6th carbon is not part of the ring. It also ends up like right there. And in addition to that, we get this carbon over here, carbon number 1, that is not part of the ring as well. We'll talk about what to do with that. But numbering wise, we also do the same thing. This is carbon 6, this would be carbon 5, this would be carbon 4, this would be carbon 3, this would be carbon 2, and carbon 1 is actually off of the ring here, which would represent this guy. So that's how we typically get to this kind of those 2 different ring type structures. And that's a good way to decide, am I going to make, am I going to make, that kind of 5 carbon ring? Am I going to make that 4 carbon ring? Any questions on that so far? And we're going to talk about how to put all the other parts on there in just a second here. All right, so let's take a look at this a little bit closer. When we do this carbon-oxygen double bond and the OH, they do become part of the same molecule. And as that ring is closing on carbon 5 and wherever that carbon-oxygen double bond is, that's essentially how we get this oxygen inserted into the ring. And that's why we don't technically have a 6-ring structure of carbons, because as it is closing in on each other, water is going to kind of come off, and we're going to get an extra oxygen that actually gets inserted in that ring. And again, for our purposes, not tremendously important in terms of that. For hexoses, the hydroxyl group of carbon 5 reacts with the aldehyde group or the ketone group. And again, wherever that is located, either carbon 1 or carbon 2 in most cases. And the cyclic structure of a D-isomer has the last CH2OH above. So this guy, usually on most of what we will see, will end up here. And again, this is going to be our carbon, really number 6 in most cases. It's always going to end up outside of the ring and above. So let's talk about how we actually get it from kind of the straight structure into the ring structure and some of the parts of it. So let's see here. Let's take a look at one here that I think they have. Just move a couple of things around. So let's say we had this guy here. And let's do OH, H, and OH. Okay, so if we are starting with this guy here, and we want to turn it into a ring structure. So the first things that we typically want to do on this is essentially we want to take this guy and we probably want to number the carbons. So we're going to number the carbons like we've been talking about, that where the carbon-oxygen double bond is going to be carbon number 1. So this would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. This would be carbon 5. And obviously this would be carbon 6. And sometimes it's helpful to take this whole thing and basically just drop it on its side. So what I'm going to do is basically just take this thing and just kind of drop it to the right. And when I drop it to the right, I'm going to end up with something that looks like this. And again, I just basically took this thing, dropped it to the right. Again, all these intersections are carbons. And I can number it, right? So when I start over here, this would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. This would be carbon 5. And this would be carbon 6. Now, when I drop this guy on his side, we have the right-hand side, right? And we have the left-hand side, right? And when I go right or left and I drop it on its side, a couple of things happen, which is important for finishing out the drawing here. First off, when I drop it to the right, everybody on the right-hand side ends up down. So right-hand side ends up down, right? Again, if you just visualize that thing dropping down, everybody on the right ends up down. Everybody on the left ends up up. So that's going to help me locate everything now. So starting at number 5 carbon, my OH is on the right, which means when I drop it on its side, it's going to be down, and the H would be on the other side. On carbon number 4, my OH is on the right, which means it will be down when I drop it on its side. And carbon number 3, my OH is actually on the left, which means it will end up on the upside there. Hydrogen will end up on the downside. And lastly here, number 2, my OH is on the right-hand side, which means it will end up down. So when we sort of drop it on its side, we are going to end up with OH groups and H groups either up or down. And again, that's the easy way to remember it. Right goes down, up goes to the left side or on the left-hand side. Any questions on that so far? So what's going to happen now is we're going to close this ring up. And to close this ring up, it is going to be carbon number 5, which is right here. It is actually going to go and find the carbon-oxygen double bond. And this is the part where you can determine how many carbons your ring should have. So that is going to be part of the ring. And this carbon would obviously be inside the ring. This carbon would be in the ring. This carbon would be in the ring, and so would obviously this carbon here. So if we count up how many circles I just did, that is 5 circles, which means you should draw the 5-member ring to start with. So right off the bat, by figuring that out, you can just simply just draw up that 5-member ring. Remember, it has a oxygen inserted in there. The other thing that we see here is what we also talked about was when we close that ring structure up, we do have carbon number 6 here that is not part of the ring. And that guy will always end up just straight up over here. And that again is carbon number 6. So we dropped it on its side. Everybody on the right-hand side went down. Everybody on the left-hand side went up. We took carbon number 5, which is really the last chirocarbon, and we closed it in on the carbon-oxygen double bond to make our ring. And now we can number our ring. So we're going to number, like we talked about before, going counterclockwise. So that guy up on top is 6, which means this carbon right here would be 5. This would be 4. This would be 3. This would be 2. And that would be carbon number 1. All right, so we're almost there. We're ready to basically place everything on the ring. Now, we obviously have placed number 6 on the ring, so we're good. Number 5, you typically don't have to worry about because that's basically where the ring comes in and closes on its shutter. So we actually skip number 5. So we really pick up here at number 4. And at carbon number 4, what we see is the OH group is down. And that's why it's important to get those guys in the right orientation. So we go to carbon number 4, draw a line, kind of a straight line-ish, and we put the OH facing down. Now, on the other end of this line is technically the hydrogen. Most of the time, people will not include it in this picture. You can if you want, but really at the other end of this line is the hydrogen. You don't necessarily have to include it, but some people may. Now we're going to go to carbon number 3, which is our next carbon. And when we look at carbon number 3, we see the OH group is up. So we're going to do the same thing. We're going to draw a line. I cannot draw a straight line here today. And then going to put the OH group going up. Again, on the other end of the line is a hydrogen. You don't have to put it. We're then going to go to carbon number 2 here. And we see the OH group is down. So we're just going to put a line here and put our OH group down so far. Any questions at this point? So that does leave us one last carbon where we need to kind of put an OH group. And you need to know, how do you know which way you should put it? Because obviously here at carbon 1, it's really intermingled with carbon number 5. How do I know if I end up or down? So usually in problems, the number 1 carbon OH group there that you put on the number 1 carbon is usually told to you in the problem. So usually you're asked to either draw the alpha, anomer, or the beta anomer. And depending on whether you're asked to draw the alpha or the beta is to where you put that last OH group. If you're asked to draw the alpha, that means that the last OH group would go down. If you're asked to draw the beta, that means the last OH group would go up. So if I took this at carbon number 1 and drew my OH there going down, this would be my alpha anomer of this guy. And I basically can draw the exact same thing and really nothing else will change here. I'm just going to draw it very badly here. Let's actually hit the carbon. There we go. And we'll go this way. And the only difference is if I drew the beta on that last carbon, we would put the OH group going up. This would be our beta. So usually they will tell you to draw the alpha or the beta. And again, that's really going to tell you the position of that last OH group on that carbon number 1. Any questions on that one there?
Just a quick question. The O in the ring is the O of the carbon number 5 in the straight line?
Yeah, so the O in the ring really comes from the combination of what happens when the ring closes in carbon number 5, where the OH is, and carbon number 1, where there's the carbon-oxygen double bond. That O gets inserted in there, and actually water comes off as sort of the other sort of product that's there, and one of those oxygens remain behind it, and it stays in the ring. And so that's why we kind of skip carbon number 5, because technically speaking, carbon number 5's attachment is actually kind of right here. If you kind of look, here's carbon number 5 is actually attached here, and then it's also attached to carbon number 1. And that's a result of when the ring comes together and closes, one of those oxygens gets inserted in, and you lose something like water along the way as well to allow that to happen. And that's why we don't really technically kind of draw anything other on the opposite side of this carbon, because it's also connected here to carbon number 6. It's also connected this way as well. And technically, there would be another hydrogen right here at carbon number 5, but it's usually not drawn in as well. And that's really where that oxygen comes in from, because carbon number 5 really has an OH, an H, and then we also have another O over here. So if you just kind of cross out, water, you're left with one oxygen. Not necessarily that oxygen, but that oxygen kind of ends up in the ring structure. Other questions on that?
So between the O and carbon number 1, leave the group when we close up the ring, right?
Yeah, so those guys, it closes up the ring between carbon 1 and 5. And like I said, there's a lot more that happens, obviously, in these processes. But essentially, you get some of this double bond kind of becomes a single bond, and that oxygen kind of gets inserted in there, and like water sort of leaves in the process and stuff like that, which is where kind of all the other guys kind of come from as well. No, so if your question is this an alpha? If it's an alpha anomer, because most of them are going down, no, alpha really just actually means that this last OH group on carbon number 1 is in the down position, while if you draw the beta one, it's in the up position. So that's it, and they will tell you basically sort of which way it goes. All right, why don't you try one here? Let's see. Why don't you do... and let's do... Okay, why don't you draw the, let's do the beta anomer of this guy. So draw the beta guy of this guy becoming a ring type structure. So take a minute or two and see what you come up with. Okay, so let's take a look and see how we're doing. So again, one of the first things you might just want to do is redraw it. And usually the easiest way to kind of do it is just to take it and basically just drop it on its side, on the right-hand side. So again, if you drop it on the right, we're going to end up with something that looks like this. We'll have our last group over here. Again, this is carbon 1. This would be carbon 2. This would be carbon 3, carbon 4, carbon 5, and our carbon 6. And as we talked about before, when we drop it on its side, again, we could renumber up here 1, 2, 3, 4, 5, and 6. When we drop it on the side, everybody on the right-hand side will go down. Everybody on the left-hand side will go up. That means that carbon number 5, I have an H down and an OH up. On carbon number 4, I got the same situation here. Carbon number 3, I got the OH down because it's on the right-hand side, H is up. And lastly, carbon number 2 here, OH is also going to be down and H will be up. Again, usually that last chirocarbon, which a lot of times is carbon number 5 here, we'll go and find wherever that carbon-oxygen double bond is, which again means it's carbon 1 in this case. That is it. If you're not sure, you could just circle the carbons involved. So that's 1, 2, 3, 4, and 5 carbons. So as soon as you figure that out, you already know what that ring should look like. Should look something like this. And just like we saw before, our carbon number 6, which is usually this group right here, is going to be left off of the ring, so it will find itself up in this area. And again, that's going to give us some location in terms of numbering. So that would be obviously carbon 6. We're going to go counterclockwise, 5, 4, 3, 2, and 1. And as we were just talking about before, since carbon number 5, which is right here, and carbon number 1, which is right here, that is essentially the top part here where it forms the ring. We skip it and we go right to carbon number 4. And at carbon number 4, we see that our OH group is up. So we will draw that up. Carbon number 3, right next door, we see our OH group is down. So we'll draw that down. Carbon number 2, we also see that OH group is down as well. And again, carbon number 1 is going to be determined based on what they ask you to draw. And in this particular case, they asked you to draw the beta. And beta is going to mean that the last OH group at carbon number 1 will go in the upwards position here. Any questions on that? Yeah, so technically carbon number 5 is drawn. It's right here. It just doesn't have anything other than really carbon number 6 sort of displayed. Again, a lot of what's left on carbon number 5 is how we sort of incorporate this guy into there. And technically speaking, there's another H coming down, not usually drawn a lot of the time. Just like, again, on these things, there's H's at all these positions. They're not usually included either or drawn. You can technically, nothing wrong with it, but a lot of times people won't draw those hydrogens in there. But you should be aware, again, it's not just an end of the line with nothing there. All those places where I just put circles, there's really hydrogens at all those locations. So technically speaking, and again, just for clarity, because it kind of gets a little crowded, people often will leave the hydrogens off of here. And technically speaking, there's a hydrogen happening right there as well. So we usually do leave that off. So carbon 5 and carbon 1 really gets sort of incorporated into the chain, and more so the carbon 5. You usually don't have to do very much of anything with that guy, again, because it's sort of in the ring formation. Other questions on that? We try. Why don't we? Where's the 5th carbon? The 5th carbon's right here in the ring, and the 5th carbon obviously is this blue guy up here and stuff. So when you draw that ring coming down this way, since carbon number 6 is up here with that line coming down, that line ends at carbon number 5, And then that guy right here would be carbon number 4. Right here would be carbon number 3, 2, and then 1. There is no OH that remains on carbon number 5, if that's what you're asking. So that kind of goes to the earlier question. So if you look at carbon number 5, there's an OH, there's an H, and at carbon number 1, there's a carbon and an oxygen. So I'm just going to kind of isolate those 2 carbons. So this is carbon 5, for example. And I won't draw out the other ones. And then this is carbon 1, right? So what that relates to is when we close the ring, this carbon and this carbon basically come and attach to each other. But in the process of them sort of closing in on each other, an oxygen here, you can see there's one oxygen here, one oxygen here. An oxygen actually gets inserted in the middle of those guys. So if you want to think about it this way, maybe just be easier to look at it that way. This oxygen sort of gets inserted between the 2 carbons, and that represents sort of this part of the ring right here. And along the way, this OH, for example, and this H is water's sort of lost along the way, and that extra H that's here also does sort of remain here. So there's sort of an insertion of that oxygen as those 2 carbons come together. And that's why we really typically don't draw anything going on there at carbon number 5 other than its connection. They like that carbon number 6. Other questions? Okay, why don't you try another one here just to make sure. Let's try this one to see what you come up with. Let's do this. And why don't you, draw the alpha anomer, see what you come up with. All right, so take a couple of minutes here, draw this into a cyclic structure, and we're looking for the alpha in this particular case. Okay, so let's take a look. So you want to kind of approach it the same way. It's a little different. It is a ketose here. So we're going to kind of take the same approach. We're just going to drop it on its side. So if we drop it on the side, we end up with something like this. A little extra line there. Get rid of that one real quick. And we would have our double bond right about there. So that would be a carbon, obviously. And if we numbered it, this would be 1, 2, 3, 4, 5, and 6. That corresponds to this 1, 2, 3, 4, 5, and 6. Now, in this case, because it's a ketose, our carbon-oxygen double bond is actually at carbon number 2, when we do want to give it the smaller number. So that's, again, why we started numbering in that direction. Everything else is sort of the same approach. We still have everybody on the right going to end up on the down. So on oxygen, our carbon 5, that is down with the OH. On carbon 4, it is also down. And carbon 3, it is up on that. So same thing's going to happen. It is going to be here, our carbon 5, which is our last chirocarbon. It is going to find, again here, not carbon number 1, but it is going to find that carbon-oxygen double bond. So again, it always goes to the carbon-oxygen double bond when it closes in. We'll see a better maybe picture of how it kind of closes in just a second. But we got 1 carbon involved, 2 carbons involved, 3 carbons involved, and 4 carbons involved in the ring. This means you actually want to draw the other ring that we saw, which is the 4-carbon ring. Kind of looks like cyclopentane, but again, with the oxygen inserted inside. Just like what we saw with the other ring, carbon number 6 is not part of it. So that guy still ends up on top here. And that is carbon number 6. We still do our same numbering. This would be carbon 5. This would be carbon 4. This would be carbon 3. This would be carbon 2. And carbon 1 is off of the ring here. And that is actually where this guy will end up. He's also off of the ring. So we're going to do our same sort of format. We're going to skip carbon 5 as, again, that is where this O gets sort of inserted into the ring. Carbon number 4, we see the OH is down, so we'll draw our OH down. Carbon number 3, we see the OH is up, so we'll draw our OH up. And now carbon number 2, we want our last OH to be alpha, which means it will go down. And actually on the other side of this, not part of the ring, is where that last carbon will go, and that is carbon number 1. So as you can see here, this carbon number 1, not part of the ring. This carbon number 6, not part of the ring. And again, we have just that 4-member ring. And because the alpha was here, we had to put the OH down, which meant our last carbon would go up. If we had to draw the beta, it would look exactly the same, except that last carbon, our carbon number 2, we would have the OH up and our carbon number 1 down if we did beta instead. So again, that would be the only difference, is the arrangement of that last one. So here, as you can see, because we went to carbon number 2, we actually had 1 less carbon in that ring when it closed up on each other. And I think I did misspeak earlier. It is actually this oxygen here that gets inserted into the ring at this position. Any questions on going from straight chain there to ring structure?
Yeah. When, for example, if in the ring, the carbon number in this one, carbon number 5, if we don't have OH, but both of them are H, so are we moving up to the next one?
I'm sorry, you kind of broke up, but were you asking at carbon number 5 if we have OH?
Both of them are H, up and down are H.
Yeah, so typically you won't have that situation because usually it will be it's usually the actually, even though we kind of go with 5 most of the time, it's usually the last chirocarbon, and that would imply that it won't have the same group on there where it closes up. So there's something like ribose, for example, which actually only has like 5 carbons. So when it closes, it is this last one. So it technically is kind of like the last chirocarbon is where it kind of comes in and closes. So you probably won't run into that situation where you have kind of the same group on that same carbon where it closes in. Other questions? Okay, so let's talk about going from the ring to the straight chain. So let me draw one of these guys. So let's say we had this guy. Just make it up here. And we got this guy like this. We got, totally missed the carbon there. Try that again. OH, we'll do OH, we'll do OH this way, and we'll do OH this way. And why don't you try to break the ring here and draw the L isomer of this guy. So draw the L straight chain. So I'll give you a chance to try to work it out yourself, and then we'll talk about how to do it. So what you want to do is take the ring here and then break it apart and make the straight chain. So see what you come up with. So we just talked about putting it together in a ring. You kind of want to work backwards. So see what you come up with, and then we'll talk an approach of how to do it. Okay, let's kind of see how you're doing. So again, a good way to do this is sort of think about it backwards of how we kind of put these guys together. Really good place to start with would be starting to number your carbons. So for example, this would be carbon 6. This would be 5, 4, 3, 2, and 1. Or you could go clockwise, knowing this is carbon 1 coming across. So we definitely have 6 carbons. So we definitely have, 6 carbons. And we know that the last one is our CH2OH, and that's carbon 6. This is carbon 1, so we'd need a 2, 3, 4, and 5. Now, how do you know if this is a aldehyde group on top or a ketone group on top? Well, if we look at a couple of examples we just did, our aldehyde group, if I drew the H, was here. And when we look at carbon number 1, there's no carbon group attached here at carbon number 1. While if we look over here in our ketone, we do end up seeing a carbon group attached over here at the end. So if we look at our ring structure here, we don't see a carbon group attached out here, which would imply that this is not a ketone, but this is going to be a aldehyde. So that's sort of how we could figure out, that we do have that aldehyde group on top and not a ketone. Typically speaking, a ketone, you will see some type of carbon group hanging out over there at the end of the ring. So now that we have that, we're going to number our carbons here. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6, obviously. Now, if you remember when we draw it into the ring structure, we drop it on its side, right? So when we drop it on its side, we end up with this sort of situation. And anything that is on the right-hand side, like we talked about, ends up down. Anybody on the left-hand side will end up up, if you remember. So if we look at coming back here, we're going to actually skip carbon 5. Again, we're going to talk about how we get to carbon 5 in just a second. We're going to go to carbon number 4. And at carbon number 4, our OH group is down. And what we know by that is if it ended up down, it had to end up on the right-hand side to start with. So that is where we would put our OH group at carbon number 4. Carbon number 3, we see the similar thing. OH group is down, which means before I put it on its side, it probably was on the right-hand side. Carbon number 2, OH group is up, which means it would end up on the left-hand side. So that is how we could kind of fill in all of our other carbons with our groups. Now we still have one carbon that we actually skipped here, which is carbon number 5. And that's going to be determined based on what they asked you to draw. So they asked you to draw L, and L means that our last chirocarbon, the OH group, is going to be on the left. So that is how we know our last OH group here will be on the left because that is what they asked us to draw. And that would be our straight structure coming from our ring structure. Question on that one? Let me draw another one and give you a shot at doing one more here at least. Let's do with, let's go with, so let's do this one here. And why don't you draw the D straight chain of this guy? And thank you. Yes, I'll learn my left and right here. So I did make a mistake here. Thank you. You know, I'll learn left and right eventually here. So I think I said it correctly. I just put it on the wrong side. So obviously L is left. So that should be left and that should be right. Maybe it's backwards if from your perspective. Thank you. So it should actually be over here since it was left. Yeah. Thank you. Next week I'll work on counting 1, 2, 3 and stuff. Okay, so let's take a look. So we can take the same approach. We see this sort of 5-ring structure. So that's going to be carbon 6. That'll be 5, 4, 3, 2, and 1. So again, we do know that we are going to go with 6 carbons here. We also, again, know it's going to be the aldehyde group on top. We don't see any carbon type group over here. So we'll come down this way, put this guy at the end. That's going to be carbon 6. That would obviously be carbon 1. And then we have 2, 3, 4, and 5. So that is 2, 3, 4, and 5. All right, so doing the same thing, we're going to skip number 5 here. We're going to go to number 4. And we do see the OH group is up. So remember, up means left. So I'm going to try to put that on the right side. That should be this way, I think. Number 3 is down, which means right. So it should go here. 2, which is down, should also go right, which is there. We'll fill in our H's on this guy. And our number 5 will be determined by this. So D is right and that is where we would put our last OH group there on our chirocarbon. So we should look something like this. Any questions on that? I think I got my lefts and rights hopefully correct. Any questions on that one? Okay, so you do need to be able to obviously draw the straight chain. You need to be able to take it from the straight chain to the ring. Any questions on how to do that? Just to touch upon sort of maybe an earlier question as well before we kind of move on from this. You know, let's just say we had something like ribose, maybe something like this. And let's say we wanted to turn this into a ring structure. So we would do the same approach here. We would dump it on its side. And this would be carbon 1, this would be carbon 2, carbon 3, carbon 4, and carbon 5 in this case. So this is 1, 2, 3, 4, and 5. Same effect. It looks like all of our OHs on the right, which means all of our OHs will end up down when we do this. Now, when this guy actually goes to close the ring, it is not going to be carbon number 5. Carbon number 5 here is actually an achiral carbon. So we actually would back up again, technically speaking, to the last chirocarbon, which would be carbon number 4. And it would be this guy that goes again to our carbon-oxygen double bond, giving us 1, 2, 3, and 4 carbons as part of the ring. So when this guy closes, it actually will make that 4-carbon ring. And just like before here, carbon number 5 will actually be above the ring. And again, this would be carbon 5, which makes this carbon 4, carbon 3, carbon 2, and carbon 1 in this case. And we again would skip, in this case, carbon 4, because that's where the ring closed. So carbon 3, the OH would go down. Carbon 2 there, the OH would also go down. And obviously the last one would be determined by what you were asked to draw. So we'll draw it down, which would be the alpha. So this is an example here. Obviously, it doesn't have 6 carbons, and it's an aldehyde group, and it makes this 4-carbon ring. So we do oftentimes think about it as always carbon number 5, but not 100% of the time. It definitely is always carbon number 5, usually when you have a 6-carbon sort of carbohydrate. But in this particular case here, we don't have 6 carbons, we only have 5. So technically speaking, it should be really the last chirocarbon that goes to that carbon-oxygen double bond. By the way, if we started with this as a ring structure, we would also know it's an aldehyde because, again, we do not see any carbon group there, so we know we should have this aldehyde group. Any questions on that particular one? Okay. So this is pretty much the steps we just talked about, so I'm just going to kind of scroll through it. Again, you can look at it again if you like, drop it on its side, collect it over there, make our ring structure, and then obviously either our alpha, which means that last OH group down, or beta, the last OH group up. Those are sort of our steps. So here's sort of how the ring sort of forms. And again, there's a lot going on that, you know, it's not really important for our class. But again, I sort of misspoke there. It is the OH oxygen there that does get inserted in the ring, as you can see. And there's really some other processes that occur, but eventually what happens is this hydrogen sort of slides its way over here and makes that OH group there on carbon number 1 in that particular case. And again, there's a lot of things being made, like water, things leaving, things coming back on. But ultimately, this is why when carbon number 5, we really don't draw an OH on it because that oxygen really does get inserted in the ring. You can see here that they did draw the H that's there, as I mentioned earlier. There is technically an H, and then again, not also drawn a lot of the times because it just gets a little crowded with all these H's drawn. You can draw it, it's not wrong, but a lot of times people will leave these H's off in these pictures, so it's not so much going on. And when we look at these sort of ring structures here, glucose, for example, most of the time is in the beta sort of conformation with the OH group up, and a little less of the time in the alpha conformation. And it kind of opens and closes as it goes through there. It makes a hemiacetal as we have our OH group and our oxygen carbon group that's attached there as well that we talked about. Here's fructose, and again, we kind of drew fructose, and we see our ketone group. So again, this carbon to this carbon giving us 1, 2, 3, and again, our 4-member ring where this group again ends up outside of the ring. This group also ends up outside of the ring. Again, our alpha and our beta conformation for it. And I think we actually drew that one earlier there on the other page. All right, so we did a couple of these, I think, so we're good. So I'll just show them. All right, any questions on sort of drawing those things, just to make sure? All right, so let's talk about some of these properties of monosaccharides. Monosaccharides are considered reducing sugars. Reducing sugars are ones that have the carbonyl group that can oxidize to a carboxylic acid. So very similar to what we saw in organic chemistry. We have an aldehyde group, right, that basically can go off and make that extra oxygen in there, and we get our carboxylic acid. You can use something like Benedict's reagent, which will obviously change color from blue to sort of that orangey reddish color to indicate that this process has occurred. And it includes pretty much everybody, glucose, galactose, and fructose that are reducing sugars. As you can see here, kind of the exact same, really, if you want to relate it to organic, the aldehyde going to our carboxylic acid. Right, and in that case, as we talked about, there's that insertion of that oxygen in there, giving us our carboxylic acid group over here. And again, that's what's referred to as reducing sugar, which means that the copper gets reduced, gains an electron, goes to copper 1, and turns that reddish or orange type color. All right, I'm not going to worry about that, I think. I'm not going to worry about that as well. So again, this is very similar to really the organic relationship here. This is basically a alcohol carbohydrate. So there's our alcohol group, which again, if you oxidize it, becomes an aldehyde, primary alcohol. And if you oxidize it one more time, as we just saw, we get a carboxylic acid basically. So these carbohydrates, because they have really these organic groups, they really can sort of go through very similar reactions that we saw in organic chemistry. And that's basically our primary alcohol going to our aldehyde, going to our carboxylic acid, essentially what's happening there if you look across the top. All right, so let's talk a little bit about disaccharides. Disaccharides are really the combination of two monosaccharides that are put together. The resulting way that we put these guys together is basically we remove water. So basically water comes out, we have one monosaccharide, two monosaccharides, and out comes water, and they basically join together through the loss basically of the water. So there's three different ones that you do need to be aware of. So this is a good slide here. You need to know that maltose is made up of 2 glucose units. Lactose, as we will see in just a second, we're going to look at each of these in just a second, is made up of glucose and galactose, and sucrose is made up of fructose and glucose. So you do need to know the 2 monosaccharides that make up these 3 disaccharides together. So let's take a look at each of these kind of individually. Maltose. Maltose is a disaccharide, is known as malt sugar. Again, it's composed of 2 glucose units, and it is made by taking out water, basically. When we take out water from these 2 glucose units, we get a special type of bond that you need to be aware of, and that is what is known as a alpha 1,4 glycosidic bond. We're going to see a picture of that in just a second, and I'll show you what it kind of looks like. But the linkage here that we have with maltose is an alpha 1,4 glycosidic bond, and it's pretty much what the kind of name sounds like. It's carbon number 1 and carbon number 4. That's where they come together. That's where we lose water, and that disaccharide basically bonds. It's used in cereal, candies, and brewing. It's found in both the alpha and beta form here. So let's take a look at how it's put together. So here's our 2-glucose. This is carbon number 1 on one of them, and this is carbon number 4 on the other. And these are our 2 guys that we lose water from. So if we just keep track of all the math, we have 2 H's and 2 oxygens. We lose 2 H's and 1 oxygen. That leaves 1 oxygen left over to basically be our linkage between the 2 carbohydrates. This is called alpha 1,4. Alpha because if you remember, the alpha conformation is coming down. And here at carbon number 1 on this guy, our OH group is coming down, which is the alpha. So that is where that alpha part of the name comes from. And it's at carbon, again, 1 and 4, which is where this part of the name comes from in terms of the linkage. Good way to remember it is alpha comes down. If you look at this bond, it's kind of coming down when you look at it towards the oxygen. And that's a nice way to kind of remember it as being alpha. The oxygen almost ends up in this kind of downward position between the 2 rings as they get connected. So this is the alpha 1,4 glycosidic bond. It is made by removing water from 2 glucose units and basically squishing those guys together. Another important disaccharide is lactose, and lactose is made up of a galactose unit and a glucose unit. And it is held together by a different type of bond. It is held together by a beta 1,4 glycosidic bond. And again, you need to kind of know that or be able to recognize it from looking at the picture. Same thing going to happen here. That's carbon 1 of one guy, carbon 4 of the other. Our water is going to come out of those 2 guys. And when it gets connected, it is going to leave 1 oxygen still there as sort of our connecting part. And when we look at carbon number 1 here on this guy, our OH group is up, and that is the beta conformation, and that's why it's called beta here. And 1,4 again is the positioning on the ring of where those guys come together. And this guy looks different than our alpha. This guy kind of goes upwards, if you will, between the 2, just like beta means up, right? So that's a good way to remember that. Again, that looks very different, the way that comes together, than what we saw here with our alpha, where it kind of looks like it is coming downward here. So that's a good way to kind of keep those in mind. So lactose, galactose, and glucose coming together, the removing of water, and makes this beta 1,4 that's obviously found in milk and so forth. And some people obviously are lactose intolerant. They can't really kind of break that bond in their body, and it obviously creates trouble. The last disaccharide that we're going to talk about is sucrose. And sucrose is a combination of a glucose and a fructose molecule. And it also has a different type of bond. It has what is referred to as a alpha beta 1,2 glycosidic bond. And that is a lot going on. So why is it alpha and beta? Well, when we look at the glucose here, it is going down, right? So going down is beta. And over here, we look at the number 1 sort of guy. He is going up. And that is what is known as alpha. So because this is both at the important sort of carbons for that, the end carbons for alpha and beta. This is carbon number 1 for glucose. This is carbon number 2 for our fructose. And that is where the numbering comes from. Alpha, beta, 1, 2. We don't have the 2 sort of symbols, alpha and beta, in these guys because this guy in the previous one is the alpha carbon and is not the one that's involved in the bond. But on this guy, when we're dealing with fructose, it is the carbon that is either the alpha or beta carbon, just like this guy is the alpha or beta carbon. And that's why we have both of those symbols related here. Alpha for our glucose, beta for our fructose. And again, the connection being between carbon number 1 and carbon number 2. Again, we remove water, leaving an oxygen behind to be really the sort of binding part of all that, if you will. Any questions on that there?
Is it the first one of the lactose is the alpha lactose or beta lactose?
For the previous one, it is actually on the galactose here is where the alpha, I'm sorry, the beta carbon, if you're asking. Is that what you're asking, this one right here?
No, I mean the lactose, like after the galactose and glucose form together, and like because I saw in here it said like the alpha lactose, so which means this formula, this structure is the alpha lactose, right?
Yeah, it's alpha lactose because when it connects together, it would then be looking at this guy here, which would be the last one, and that OH is down.
Okay. So
the connection, the kind of whole molecule together is now lactose, basically, right? Without the water, obviously. And when we're looking at the alpha or beta, it's really the last carbon all the way to the right, if you will. And on that last carbon all the way to the right is the OH down, and that's where the alpha comes from the lactose part, if that's your question.
So which means in here it's the O in the middle when they form together, it doesn't matter, right?
That O comes from well, you can use that O to identify it as the bond that holds those two units together as beta, because it kind of goes up. So there's kind of two indications here. This beta 1,4 is referring to the actual bond here between the two, and that's what that beta refers to. And that's because it comes from the beta OH group off of here when it comes together. Then once it actually comes together in this big box that I just did here, the entire lactose molecule could also be identified as alpha or beta, and that's based on this last guy over here. Does that make sense? Yeah.
Okay, yeah. So which means if we just to determine whether it is the alpha lactose or beta lactose, it's only the carbon number 1, right?
Yeah, so it's usually on all these sort of cyclic guys, for lack of a better drawing, like that carbon's all the way to the right, usually on the picture, you know, which way that OH group is going. But for us, in terms of what you need to know, it's not necessarily the whole thing when it comes together, is it alpha or beta? You need to be able to identify sort of that linkage and that bond that happens between them as being either, you know, alpha, beta 1,4, or whatever we've been kind of talking about in terms of that. Other questions? So just to give a little closer one, since this is sucrose, just to illustrate that, one last here to finish up. That is 6, that is carbon 5, that is 4, 3, 2, and 1. And coming this way, this is carbon 6, 5, 4, 3, 2. And this is why we have our sort of numbering like we saw there as our alpha, because really this guy has the OH group coming down originally, as you can see here, and alpha 1, and this guy has the OH group coming up, which is our beta, and that's how we get our alpha beta 1,2 bond here between carbon 1 and carbon 2 in this linkage. And again, for us, you really need to know how to identify that linkage between two carbohydrates as being either alpha 1,2 or beta, whatever it may be. Obviously, if we want to break this apart, we got to throw water back in there, and we get our two monosaccharides that basically pop out in that particular case. Any questions on that there? All right, I guess we will stop there today, I guess. We have an exam on Monday, so no lectures. You'll take the exam like we've been doing during lecture time. Again, it will cover all the organic stuff. It will cover also chapter 8, which should be acids and bases. And then we will come back for one last lecture day there on Wednesday. It'll be a big lecture day, I imagine. And we'll finish up the last little bit of the final 2 chapters. Again, we're not going to cover everything in those chapters. We're just going to cover a few things that are of importance. All right, any questions on any of that stuff?